Hello everyone, thank you for being here. In today's presentation, I'll be covering how we leverage automation for data mining, pre-processing, and curation. To give a general overview of a cheminformatics machine learning project, the very first step is data mining. This is where we collect data from commercial public databases and literature. And then we do data pre-processing. Most of the time, the data we have collected is very noisy, messy, and contain irrelevant data and can come in different formats, so it's not ready to be used. In this part, we deal with those complications and transform the data into a useful, efficient format. Then we do data curation. In this step, we make sure the dataset is high quality, containing only biologically relevant and useful information to the endpoint that we are modeling. We do mistake diagnosis and correction because there are usually many mistakes in the databases, and a machine learning model cannot be better than the data that is built on. The three steps that I have described related to data handling usually take a huge chunk of the project timeline. They are in fact the most heavy lifting part of the entire pipeline. Next, we generate molecular or atomic descriptors and do feature engineering as needed. Then we split the data into train and test sets. This can be done using different approaches, for example, random splitting, cohort mapping, and so on. Next, we select a machine learning algorithm, such as support vector machine or artificial neural network. Then we move on to model building and validation. Based on whether it is a classification or regression problem, we choose proper evaluation metrics and select the best models. Lastly, we assess the applicability domain of our models. Among all the steps, handling data is the most cumbersome of all, and the process of data mining, pre-processing, and curation normally take about 85% of the work and the project timeline. So during the data handling, we often use automation for efficiency. But not only that, we use it for tasks that are tedious, redundant, exhausting, and time-consuming for humans. We use automation to improve the quality of our work and to minimize human mistakes. We can use automation to address common problems in the pipeline that require a clear, well-defined set of rules. Below are a few example cases where we use automation in the pipeline. Like here, structural retrieval, rule-based information mining, handling duplicates, flagging suspicious entries, and so on. I'm going to show 3 use cases of automation from a project that we were previously working on, which is the site of metabolism for cytochrome P450 project. The first case is where we apply automation to do web scraping for drugs from the FDA website. When we look at the FDA website, they have approval drugs listed and categorized by year. They have more information at the top, but this is the table that we are interested in extracting. So in the pipeline, given a range of years, we can extract all the tables, including the drugs and other information. But not only that, each drug has a hyperlink that can give more information about the drug. So when you click on it, you'll be directed to another link. And on that page, you can see other hyperlinks and additional information. But what we are interested in is this labeled PDF document because it contains CYP-related metabolism information. So when you click on it, it will open a PDF that is searchable, and we already have a list of keywords for the 9 major CYP enzymes such as CYP1A2, 2C9, and so on. So we use those keywords to search the document. If they are there, the automated pipeline will collect those keyword matches, and based on that, it determines how important the drug is for our site of metabolism project. All the steps that I have mentioned here are included in the automation pipeline. So as the output, we have the CSV file along with drug names, information, keywords, and priority assessment. From these results, we focus our literature mining efforts on the high priority drugs because we know they likely have more resources for CYP information and metabolism schemes. This saves a lot of time, efforts, and headache that would otherwise be devoted to low-priority drugs for which CYP information is too challenging to find and eventually would be dead ends. So to summarize here, this automation pipeline efficiently mines hundreds of drugs and help us prioritize which drugs that we should hand down, and this automated process is carried out in just minutes. The next use case that I want to show is how we use automation for structural extraction and verification. Sometimes the chemical datasets would have names but no structures reported. Sometimes the structures are reported but contain multiple mistakes. So we often use this automated pipeline in many cheminformatics projects. So what it does is take a list of names. For example, like here, toluene. Then it extracts structures based on the chemical name from multiple public databases using APIs. Then they go through structural cleaning and standardization, such as generating canonical smiles, standardizing tautomers, removing salts, generating inch keys, and so on. Then, when the process structures are ready, they are compared and categorized. In this example, they are all the same, so toluene would go into agree category. If the results are different, it will go into suspicious category. If only one or two databases have the structural information, it will go into not enough info category, and if no database reports the structure, it will go into nothing here category. The structures in these categories need more work because we will have to do manual assessment, do more digging, and then we resolve the issues. Normally, we will feed a list of chemical names into the automation pipeline like here. Then we would have an output CSV file like that. It contains structures from different databases along with the verification results. So to summarize this case, thousands and thousands of structures are extracted and verified using this automation pipeline. It helps us improve the quality of our chemical datasets, and it is integral to our data curation pipeline. The last case I want to show is how we use automation for merging datasets. Of course, each project is different, and the way we want to merge and format data is different as well. This example is specific to our cytometabolism project. Here we have 3 databases. We have already processed them to have similar formats at this point. If you look at the first one, it contains structures, IDs, smiles, atomic sites for each CYP enzyme, and for example, here is for 1A2 CYP enzyme, and these are the atomic sites of metabolism associated with that 1A2 enzyme. And we have those for 2B6, 2C9, and so on. You will also notice the strange formats like 2 commas here, but of course, we account for them and address them in the automation pipeline. Now we are merging data like this from different databases, and there are going to be chemicals with conflicting information, so we need to address that. When merging, we have these rules in mind for handling duplicate structures. We'll merge sites of metabolism for the same CYPs and also the information in the other columns. We'll also correct and format the delimiters so they are all consistent. We'll keep the second or third IDs in alternate name column, and for conflicting CYPs, we'll flag them as suspicious so we can manually go and check them after. Here is the entry from database 1 and 2. They are duplicate entries based on the smiles, and as you can see, there are several conflicting sites. For example here, 78 for 2A6, 71 for 2B6, and there are more conflicts in 2C9 and 3A4 as well. So when we merge them, we combine the atomic sites for each CYP. It also sorts them and separates them by commas. The second ID is moved to the alternate name column, and references and data sets are merged together like here. We also need to flag the conflicting CYP info, so wherever the atomic site information is different, the relevant CYP enzymes are noted so they can be manually checked later. So the automation pipeline includes this extra column which keeps track of CYP enzymes with conflicting atomic sites. Here I'm showing an example case for a pair of duplicates just from 2 databases. In the actual merging, there are hundreds of duplicates from several databases that we need to resolve. As you can see, the task involved in this process can become very redundant, time-consuming, and highly susceptible to human mistakes. It will be quite painful to have to deal with them manually. This automation pipeline is very efficient because it handles all the merging in a few seconds while following consistent rules and addressing all the complications in the process. To conclude, I have shown 3 example use cases of automation from cytometabolism project to highlight the efficiency, usefulness, and importance of automation. We often use automation in data mining, preprocessing, and curation to help with the workload. The goal is to reduce tedious, exhausting, and time-consuming tasks, basically to ease the strain and burden on humans, to diminish human errors and mistakes, to enhance data quality, and of course, to improve efficiency by saving time, money, and effort. Last but not least, I would like to convey my thanks and appreciation to my team members. We have a pretty good collaborative cheminformatics team. Many special thanks to Pankaj for his mentorship, kind help, and support for all the projects that I have been working on. Michael, Bob, Marv, David, Robert, Vieira, Eric for helpful guidance and fruitful discussions, and also John for giving me opportunities to work on exciting projects. I don't want to leave out an important partner as I end this presentation, and this is my cat Linux. He is a faithful companion and devoted partner who likes to be on my desk as I work, so thank you, Cat, for your company and contributions as well. And lastly, thank you to the audience for your kind attention. Please let me know if you have any questions.